And we're back. Welcome back and happy Thursday. Today, we're going to look at methods for constructing Bayesian networks. Before we talked about evaluation and what the semantics are, and we're going to focus today on Bayesian network construction. But before we do that, some administrative bits. The algorithm in particular for doing that construction in an automated fashion of Bayesian networks is called the K2 algorithm, at least one of the many algorithms. That's our focus for today. There are two different publications. Those are the URLs. I will also have them on the course Blackboard. There's a journal publication that is much more expansive, and then there is the conference version, which is much shorter. So please read the conference version, and as a reference, go to the journal version for more detail. Okay, so where we left off last time, we talked about a Bayesian network, and we said it's a graphical model, a directed acyclic graph, where the edge direction represented causal dependence. And so we arranged it in a tree structure. We talked about its complexity dependent on the number of parents for a particular node. And we said the CPT, conditional probability table, has 2 to the n+1 entries, assuming the simple case of Boolean variables. Of course, if there are more than Boolean variables, that base, instead of 2 to the n+1, it would be however many levels or values a variable takes on to the n+1 power. We also talked about these dependencies as representing factors that we can use to simplify the joint distribution, giving you your feature vectors and your class labels that co-occur with one another. And so in essence, we can pick a factorization, and that's effectively what we're encoding when we describe a particular set of dependencies, causal dependencies, for the Bayesian network. And so we talked about the reasoning, and this is a powerful approach because you can set as evidence any variable or node, and you can treat as a query any variable or node, and with the same network or the same data structure, it's a graph, a DAG, you can get all sorts of different types of reasoning. And we talked about diagnostic reasoning, we talked about predictive reasoning, and intercausal reasoning, using the lung cancer network example. Okay, so let's get into the Bayesian network construction. And so a Bayesian network is, when you think about it, a general form for factorizing or factoring a large joint distribution into the product of a set of conditional distributions. And we said when we do that, we're summarizing this joint distribution using simpler, smaller distributions. And so essentially what we have from a Bayesian network, the probability of the joint vector x1 through xn, so you have n many features, is nothing more than the product of the independent factors, which are the probability of each node given pi I, where pi I are the parents of each node. And so we have this factorization as the product of these conditional probabilities, each node given its parents. And so if we were to take this lung cancer network that we carried from the previous example from the last module, would say the probability of joint vector, pollution, smoker, cancer, X-ray, dyspnoea is equal to the probability of pollution, it has no parents, times the probability of smoker, it has no parents, times the probability, conditional probability of cancer given pollution and smoker, because of cancer's two parents, pollution and smoker, times the probability of X-ray given cancer, times the probability of dyspnoea given cancer, because dyspnoea has a single parent, namely cancer. And so if you were to do out the math, expanding out the product rule and so forth, you would actually be able to get back to this joint distribution from the product of each one of these factors. Okay, so let's look at an example Bayesian network. Now, in this Bayesian network, it's just a linear chain. We have node x1 in influences x2, which influences x3. And so each one of these nodes we're going to assume has two values, binary values, a categorical, present and absent. And for this network, we're going to assume we have these 10 cases, and cases are the name for data vectors. And so here are the cases. For example, the first case, x1 is present, x2 is absent, x3 is absent. Likewise, up to the 10th case, x1 is absent, x2 is absent, x3 is absent. And so we take this Bayesian network and we run this data. We can do that through this Bayesian network. And actually, given these settings for x1, x2, and x3, we can count the number of times we get for each of these conditions, x1 present, x1 absent, x2 present and absent, given x1 present, likewise x2 present and absent, given x1 absent, and x3 present and x3 absent, given x2 present, x2 absent, and x2 absent, x2 absent. And so literally, how we calculate each one of these probabilities associated with the CPT is for the filtering probabilities, conditional probabilities, we'd set our condition. We would eliminate from consideration those examples for which the condition is not satisfied, setting aside those for which it is satisfied. And then for what remains, we say how many of them, express that proportion, how many of them have x2 as present. And so, for example, if we said x1 is present, given x1 is present, well, that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 cases where x1 is present, and for how many of them is x2 present? Okay, so out of 5, that's x2 is present for this one, it's present for that one, present for that one, present for that one. So it's 4 out of 5, which is 0.8, and that's where we get our 0.8. Okay, so for this Bayesian network, given the causal dependencies, we can perform counting among the cases, 10 of them here, and fill in all of these CPT values as well as the prior values. Okay, and so we have our database, and let's assume we have two different Bayesian network structures. They're the same three nodes, x1, x2, and x3, but this is our first Bayesian network structure structure 1, and it's that linear chain from before. And then we have this V structure, this branching Bayesian net structure 2. x1, it causally influences x2, and x1 influences x3. You could say x2 is causally dependent on x1, and x3 is causally dependent on x1. Okay, and then lastly, we have the same cases. So we have this database of cases, and now we want to score the networks. We want to see which network is more likely given this data. And if we can determine which network is more likely, i.e., it has the highest constituent probabilities, well, that tells us that the dependencies encoded in one network is more faithful to what the real dependencies are in the data. And so this score, we're going to depict that as the probability of Bayesian net structure 1 given the data, and the probability of Bayesian net structure 2 given the data. And now you can assume equal priors. That means there's no preference for the first structure over the second structure, but you want to know which one most closely coincides with the ground truth dependencies in the data. And how you do that is look at the probabilities associated that are possible associated with each of these networks. So the idea then is, if you want to figure out in an automated fashion what is the best set of dependencies to describe the dependencies among your different variables, x1, x2, and x3, it requires you search through all of the different Bayesian network structures you can have among these three nodes for that one that has the highest likelihood probability of the Bayesian net structure given the data. And so let's define D to be a database of cases, and cases is nothing more than a synonym for feature vector. So we have our data set, and let's define Z to be variables represented in D. So these are all the variables in our case for this example, x1, x2, x3. So Z is a set of all the variables represented in your data, and also represented in your Bayesian network structure. So now we're going to use a likelihood ratio to score them. We said the score for a given Bayesian network structure is the probability of the Bayesian network structure given the data set. So for every two Bayesian network structures, we're going to specify probability of Bayesian network structure I given the data over probability of Bayesian network structure J given the data. Now, of course, if this expression, this ratio, likelihood ratio, is greater than 1, it means that the probability of Bayesian network structure I is greater. If this expression is less than 1, it means the probability of Bayesian network structure J is going to be greater given the data set. So now we take our definition of conditional probability. We get the joint distribution between Bayesian network structure I and the data set over the data set's probability. And then in the denominator, we get the probability of Bayesian network structure J jointly with the data over probability of the data. Now, of course, there's a common denominator here, and this D is going to cancel. And then we're left with this joint likelihood ratio, probability of Bayesian network structure I and D over probability of Bayesian net structure J and D. And so this likelihood ratio is jointly between the Bayesian network structure and the data. All right. And so how do we efficiently compute this score then that'll tell us which Bayesian network structure is most appropriate for the ground truth underlying relationships, causal relationships between the variables that are given? And so you assume that the variables in your variable set are discrete. That means that they're quantized to some levels if they're real valued. And you have individual cases or data vectors that are independent of one another. So each one of these rows from our data set, they stand alone. One feature vector value does not influence another feature vector value. They're independent from one another, these cases. Now, of course, because they're independent, that simplifies how you aggregate these scores. And then we also make the assumption of completeness. There are no missing variables. So if you have some data set, we have missing variables, you can assume a priori that you've done data cleaning. You've either interpolated those missing values or you've eliminated those records. So the data has been cleaned up already. You can make that assumption. And so let's assume that the following density is uniform. The BP, given the Bayesian net structure, you can assume that's uniform. And BP is the conditional probability for the assignments associated with a Bayesian network structure. So that means if you have an assignment probability of some node xi given some node xj, and let's say xj can take on values of, let's say, true, false, and xi can take on values, for example, low, medium, and high, you can assume that there's no preference for low, medium, or high above the others. They're equally likely to be selected, low, medium, high, and likewise true is equally likely to be selected as false. That's the assumption that we're working with. And that's what is meant by this BP, the conditional probability associated with the assignments of values for variables, both the variables and their parents, in the Bayesian net structure. And so all variable values are equally likely, and all Bayesian network structures are equally likely to be selected. So that's the assumption that we're working with here. So let's see how we efficiently compute this. Now I'm going to spend a little bit of time on this notation because it'll be really important to understand what it's doing in when you read through the conference publication for this and the journal publication. So BS is the Bayesian belief network structure, and it contains all the variables in your variable set. Now, xi is a variable. It's the ith variable. Here, I goes from 1 to 3. We have 3 variables. And the size of our variable set G in our example here is equal to 3. Now, xi is a variable, and variable xi can take on a number of values. That number of values is called Ri. So if we took all the values that xi can take on, well, xi, its value is drawn from some set, and that set, the first value is the first value vi for xi, and then vi I2 is the second value, V for variable I, the value number Ri is the last value it can take on. So if we were going to look at that set here, the cardinality of that set of values that the ith variable can take on is going to be Ri. And so Ri is the number of different values that a particular ith variable can take on. Now we also have pi I. Pi I is the set of parents of variable xi. Now, of course, pi I is going to have an upper bound. Either a variable has no parents, that means it's a root node, or a variable can have n minus 1 parents. It has n minus 1 parents if all of the other nodes are parents of that single variable. So if we had n variables, here is variable 1, for example, and if its parents are variable 2, variable 3, variable n, well, that means pi I, pi 1 for this variable is equal to variable 2 through variable n. And the size of pi I, in that case, would be n minus 1. So we know if we have n variables, pi I, that set parents of variable I, is at most n minus 1. So pi I is a set describing the parents of some variable. Now, wij. Now, we said that the parents of a variable, if we have the probability of, let's say, variable 1 given variable 2 and variable 3, well, variable 2 and variable 3 can take on values. Now, if these values were Boolean, that would be 2 choices for this one, 2 choices for this one. That would be a total of 4 different instantiations you can have for variable 2 and variable 3. You could have false, 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 true, true, false, true, true. Now, each one of the instantiations of the parents of the ith variable, i.e. pi 1 in this case, those instantiations can take on 0, 1, 2, 3, 4, in this case, 4 different instantiations. And so we're going to say the jth instantiation for the parents of variable I, that's going to be called wij. So wij is the jth instantiation of parent I, and the number of instantiations is going to be qi. So qi, in this case, there's my qi instantiation, and the jth instantiation, wij, that's going to range from wi1 in this case up through wi, the qi instantiation, where qi is 4 for this example. And so wij represents the jth instantiation of the parent set observed in the data, and there are qi of them that you observed in the data. Okay. And then lastly, we have this nijk. Now, this nijk, that's something you count from the data. And this nijk is the number of cases, right? The number of vectors in your data set. And this is important to pay attention to, where xi, the ith variable, has a value, so it's a particular value of xi, and at the same time, the parent set has the ith instantiation, the parent set of xi. So this nijk, it talks about the number of cases for a particular instantiation of the variable as well as its parents. Okay. And so then if we were to talk about all of the different values for a particular variable, we would sum together all the nijks for the first value of the variable, for the second value of the variable, for the third value of the variable, and so forth. And so here, when we sum, we're summing the number of cases in your data set for the first value, second value, third value, up to the kth value of the variable, where you have the jth instantiation for the parents. So what does this mean? So if I have probability of variable 1 given variable 2 and variable 3, if we assign a particular value to variable 2 and 3, well, that's one of these instantiations, that's the jth instantiation, so maybe that's true and false, right? J might be the third instantiation, might be the fourth instantiation, what have you. And then what we're adding up is the number of cases for given this filtering of the jth instantiation for the parents of the ith variable. We're going to look at the number of cases that have the first value, v11, the second value, v12, up to and including the last value, v1 ri. And so here we're going through the data set, and for a given parent instantiation, the condition, we're doing that filtering interpretation of a conditional, and we're looking at the number of cases where for what's left, the number that are the first value and all the different values that the query variable can take on. And that's what Nij is. Okay, so now that we have all this notation down, let's look at what this score is, the joint distribution between the Bayesian network structure, a particular one, and the data set. So here we have the prior, and we said that it's uniform. All of the structures are preferred, so there's a probability you take all of the structures. If you have 100 different structures, that's 1 over 100. Okay, so now if we look at this, remember, we're looking at the score for the entire network, and so we're considering all of the possible ways we could assign values. And so we're going to use some permutations here. And so with these first two products, what we're iterating over is the nodes themselves. So these are the variables, and we have n many variables from the first variable to the nth variable. And now here we're looking at the instantiations for the parents of that variable. And so this J here is going to talk about the instantiation for the parents. So this is the instantiation of the parents. Okay, and so for the ith variable, for each of the qi instantiations of its parents, because that's what J indexes over by the same notation, what are we going to look at? So let's look at and unpack this term. So we say Ri minus 1 factorial. Ri is the number of values that our variable x can take on. And so if it can take on Ri many variables, well, in this case, for a particular value that it takes on, if you have Ri total values that it takes on, all the values that we're not considering, there are Ri minus 1 of them. So this says the numerator for all the values different from the current value. So that says for the first variable, for all the values different from a given value, right? We look at all the possible arrangements of it. Okay. And so it says for all the different values different from what's current, we're going to look at, and this Nij says all of the cases in the data for a fixed parent instantiation, the jth parent instantiation. So this is all of the counts of the values for a variable for a given fixed instantiation, the jth instantiation of the parents. You're going to add that to the values that are not the current one. Okay, so this proportion says for a given instantiation of parents, all the values that you find in the data, all the other values, look at the different values, and then we're going to multiply, and this multiplication that handles each one of those values. So if we looked at the first value, right, that would be VI2, VI3, and so forth up to VIRI, if you're considering the first value in this summation, in this product. And so when we look at this product, that product is taking into consideration a particular value. And if we looked at these two factorials, well, we're multiplying by the number of cases in the data set where your variable takes on a particular value for that instantiation, for each instantiation for each of the values. And so here we're saying effectively for each of n many variables consider a single instantiation of its parents. And for that instantiation of the parents, we're looking at a probability, a proportion here. The arrangements of the values for that variable minus that one of those values. And we're looking at the arrangement in the denominator of values plus the number of cases for all variable values of that variable where a parent instantiation is fixed, and we multiply it by all the different instantiations. And so here it's saying how many arrangements for a given value of a variable, look at all of the arrangements that we didn't pick, divide by all of the arrangements of the cases as well as the value, and then we're going to weight that by this product, which gives us all of the values for a given instantiation of the parent. And so this last term is accounting for that one more that's missing from here, and it's also accounting for that one more here, and it's doing it from the data. And so in essence, this is a probability. It looks at the arrangement of values for a variable, and it's looking for the arrangement of values in addition to the number of cases for the values where the parent instantiation is a particular fixed instantiation, and you're doing this multiplying over all the different instantiations you can have. Because for a different instantiation, well, the other instantiations are going to be a certain amount. And so we consider all of these, and this ratio gives us a type of probability for a particular instantiation of a variable relative to its parent's values. And so in essence, this is like evaluating all of the different assignments that we can have, both of the parents, we're iterating over this super product, as well as all of the values that the variable can take on for a given value. So this inner product says choose the first value, choose the second value, choose the third value, and this product is saying for all the other values that we're not considering, both for the instantiation of the parents as well as instantiation for the variable itself. And so we multiply all that together because for the score of the network, we have to consider the combination of all possible assignments you can have of variables and their parents, and you're doing it from the data expressing this proportion. Okay, and so this is the score, and the score represents the probability given this data of all the possible assignments that you can have of values to the variables for every fixed assignment to parents that you can have from the data, and that from the data is really, really important. Okay, so this is a probability of all the possible arrangements you can have. That's what this proportion is. There's the arrangements of the variable, and there is your support from the data, and this is for each value that you get assigned from the data. All right, and so the probability of arrangement for values of a variable and its parents is what this ratio gives you. And this is the number of cases where it has its case value. All right, and so essentially then, when you evaluate and you compare Bayesian network structures, you're trying to find that Bayesian network structure. For example, is it Bayesian network structure 1 or Bayesian network structure 2? You're trying to find that Bayesian network structure that maximizes this joint probability between each of the Bayesian network structures and the data set. Okay. And so you have a connectivity matrix, and if you have a connectivity matrix that defines the graph of all possible networks, well, what does that look like? You have x1, x2, x3 for the three variable case, x1, x2, x3, okay? And you can have a 1 in a slot if there is an edge, or 0 if there's not an edge. And so that means there are 2 to the n many graphs that you can have, and that's exponential in the input description, and that's a big no-no, and it's intractable to actually do a straight search through all the possible arrangements of zeros and ones for each one of these slots. And so your solution then to reduce this is to impose an ordering. Instead of considering all possible edges that you can have between nodes in a graph, you're going to have a particular ordering of the nodes in the graph. And so is it perfect? No, it's not, but it's tractable. And so in this ordering, we're going to represent something. If a particular node, the xith node or variable in this ordering, precedes the jth node, so you have xi to the left and xj to the right, then that means an arc may exist from xi to xj, meaning that xj is causally dependent on xi. And so this idea is that the nodes that are closer to the root of the tree are on the left, and the nodes that are closer to the leaves of the tree are on the right. And so things on the right-hand side of this ordering are causally dependent on things on the left-hand side. And so this reduces, when you do this ordering, your search space to polynomial instead of being exponential in the number of nodes in your graph. Okay, and so assuming that your Bayesian network structures are uniform in their distribution, you don't prefer one over the other, each structure is equally likely, this network ordering reduces your search space from exponential down to polynomial, and now it's tractable. And so certainly you don't have to your availability for your search all the possible Bayesian network structures. You have some of them, but not all of them. If you had all of them, you can't possibly search them anyways. So having some of them in polynomial time at least is doable in a reasonable fashion. And so our network ordering reduces the search space. And now, given this uniformity over these Bayesian network structures, if you have 100 or 1,000 Bayesian network structures, well, if it's uniform, then that probability is 1 over 1,000. So we can just change that probability of BS to just be some constant when we're evaluating our score. And so this is going to be the criteria we use to score the Bayesian network structures to determine which one is a better match for the ground truth dependencies within the data set. And so you maximize by finding the parent set of each variable. And so how we're going to do this is we're going to say, okay, well, we know that the parent set is important. And so for this expression, we're going to find that particular parent for each of the nodes such that we maximize this inner expression. And so this maximization is going to occur for every instantiation of each node's parents. And so you can try for a given node, all right, is, let's say V1, and we have V2 and V3 and V4. We'd say, all right, for V1 is V2 in its parent set. So we try V2, and then we try V3, and then we try V4. Okay, and one of them is going to maximize this expression. And then after that, we know V1 has as its parent one of these nodes. Let's say it's V2 that maximizes it. All right, so then after that, we said, okay, now if we know V2 is in the parent set, let's try V3 with V2. And then let's try V4 with V2, and one of them is going to maximize. And we keep doing that, adding more parents each step along the way to try to maximize this expression. And so this maximization is going to occur for every instantiation for each node's parents by growing this parent set. And this maximization has to coincide with network ordering. And so if we order our nodes x1, x2 through xn, well, if we consider something as a parent, well, x1, it doesn't have any parent. x2, well, which ones could be its parents? x1 could be its parent. All right, so if we look at x3, x1 could be its parent, x2 could be its parent, x1 and x2 could be its parents. And if you look at x3, that's x4, well, x1 could be its parent, x2 could be its parent, x3 could be its parent, x1 and x2 could be its parent, x2, x3 could be its parent, and so forth. And so as you look at the parent sets that you consider for each node, you also make sure that these parent sets coincide with this left to right ordering from root to leaf in that list. And so a node then can have at most n-1 parents. And if you do that, of course, that makes it still exponential, even within this list, because we have to consider xn with one parent, with different combinations of two parents, different combinations of three parents, and so forth. But we can make this a lot more tractable further by limiting the parent set to U many nodes. And let's assume, in this case, we assumed U is equal to, say, 3. So when we say, okay, for x2, right, x1, is that its parent? Okay, it respects U. Let's say x4. We'd say, is x1 its parent, x2 its parent, x3 its parent? And then consider 2, and then consider 3 of them. And then for the next one, we'd say, all right, well, if U is equal to 3, we only consider, is this its parent? Is that its parent? Is that its parent? Nope. And you only consider a parent set of a maximum size, and that limits the search that you're trying to do when you're trying to find parents for a particular node. And so you can limit the parent set to some number of nodes. And then as a greedy approach, you start with one node at a time, incrementally add parents to its parent set, and see at what point do you maximize this inner expression related to the different parent instantiations or parent set of a particular node, one node at a time, in list order from left to right. And so you stop adding more parents when one of two things happens. It fails to increase that probability score, that's the inner expression for the structure, or you reach U, the limit on the number of parents you can have. And so you're selecting the U many best parents for each node incrementally in its parent set, respecting parents that are to the left in that ordering of your n many nodes. This algorithm has a name. It's called the K2 algorithm, and you start out with n nodes that you input and an ordering on the nodes. Now, it takes polynomial time to do the ordering, and so that's included in the runtime of the algorithm. And you also input an upper bound U on the number of parents, i.e. the family size. You also input your m many cases for your database. And so you start out for each node. So we have that loop here, for loop. You start out with an empty parent set, and you begin bootstrapping with the old score is just the family score for each of those I nodes given the current parent set, which is empty. So that's just your bootstrap. So then you start out and you say, okay, well, let's go and we're going to limit our parent set for the ith node to U many nodes. And you start out with Z. It's a node in the predecessor list for the ith node. And in that predecessor, you're looking for that family that maximizes the family score. And so you start out, if you have some node xi, and you have some node x1, and you have some node xi plus 1, xi minus 1, and we go up to xn. And now for the ith node, if we're looking at the node z, is going to be that predecessor that maximizes the family score for that proposed new family, including that parent. Well, the predecessor list of the ith node is going to be all those nodes, xi minus 1, I minus 2, up to and including x1. Now, of course, if we are only considering those in the predecessor, well, all of those edges that we propose, if we look at this loop, we're going to go through and say, okay, is it this first node, xi minus 1, is it xi minus 2, xi minus 3, and so forth. And you're going to look in that predecessor list. And so this evaluation is going to be 2 to the size of the predecessor list. And you're going to limit the number of parents to be U. And so you're going to go back to that predecessor list, looking for the one that maximizes the family score. And once you find someone that maximizes the family score, well, you're going to run over some number of nodes, I minus 1 many of them. And so for that, well, that's very doable in polynomial time because you're only going to search up to a certain number going back in the past. And you're going to propose then a new score, which is the family score, assuming added to your family, it's augmented to include that new parent. And so you're going to go through, and then you're going to see if that new score improves upon the old score. And if it does, you accept that new score, and then you update your parent set to include that Z. And so here on each iteration, we say let Z be the node in your predecessor list, that maximizes the family score. And so you can do this by looking at the immediate predecessor, and then the one before, and the one before, and the one before. And then you're only going to add enough predecessors until you have u. So that's going to be 2 to the u. And since u is fixed, that is polynomial. So we have this step in this while loop that runs in polynomial time. And we have for this is n many times for your nodes. Well, that runs in linear time. We have linear in n. And for each of these n, we're going to have 2 to the u. And so that is n many times 2 to the u, which is absolutely big O of n to some polynomial k. And so this runs in polynomial time. And so you keep doing that for every single node until you end iterating through all of the xi nodes in that particular ordering. And the cost you pay for that ordering, that sort, is also polynomial. So we have the cost big O of n to the q for the sort, and then you add that cost of big O of n to the k, which is n times 2 to the u, and therefore k2 is polynomial runtime and therefore feasible. That's all I had. We'll end there. Please make sure you're keeping up with the reading. And as usual, have a great weekend. Please stay healthy, stay safe, and I will see you all on Tuesday.